we have seen that the size of the object has an impact on contrast. There's a second consequence, and that is the impact of scattering on contrast to noise ratio. And I want to address this question: how does X-ray scattering impact the contrast to noise ratio? Let's look here at an idealized situation. We have an X-ray source. I will, for simplicity, assume, as we do for the entire course, that the X-rays are coming in a collinear, coplanar way. We have the subject here, and the subject here has a lesion. This is the lesion here. And now we will assume that this lesion is such that it is producing complete absorption of the photons through the photoelectric effect, and this complete absorption obviously means that the object, the lesion, is easily detected. Now let's consider the situation where we increase the photon energy. As we increase the photon energy, as we have seen, Compton scattering becomes increasingly predominant, and this produces an increased masking of the object as follows. We have the film that we detect here. Here's the idealized object here. We see it very clearly here. But now we can have photons that are being scattered by the Compton effect that are detected at this location, even though they have come this path here and then they are coming through here. As we increase the photon energy even further, Compton starts to completely dominate the mechanism of X-ray interaction with tissue. We have increased Compton events, and this leads to a near complete masking of the object. So this scattering, the probability of the scattering obviously increases with field of view. As the object is bigger, so we can have a photon scattered here and at the lower abdomen and appear at the level of the heart because it has been scattered. So with a larger field of view of irradiation, we have a increased reduction of image contrast. And the solution here is to mitigate the effects of scattering by using an anti-scatter grid, which is actually the same thing as a collimator, and collimators are something we are going to talk about next week when we talk about emission computed tomography. So let's look at schematically what this anti-scatter grid or collimator is doing. We'll presume we have a detector here at the bottom, and then we have two thin stripes. In this case, we'll idealize it. This is not the complete situation, but to idealize the principle, this is some material that has a very high atomic number Z and a high electron density. We can idealize it. It's not the perfect situation, that this is a material that is capable of stopping the X-rays. So the X-rays are coming nearly collinear, as we would like to have it here. They come in, they're still passing in, they're detected by the detector. For X-rays that are being scattered by Compton, that is these X-rays here, here and here, they don't have the proper angle, so they are not coming in a collinear fashion. They hit this collimator material here and they are being stopped, so they cannot penetrate, and so they are being eliminated. In the real world, a collimator grid looks like this image here. So it's a hexagonal structure, has a certain thickness, and this does ensure a certain directionality of the X-rays. This collimation principle is a brute force way of establishing the directionality of the X-rays. If there's a way we could detect the X-rays, not only just the X-ray, but also say, well, it came in this direction or that direction, this would be the perfect experiment to do. We wouldn't need it, but this is not very easy to do. So this is a brute force way of establishing the directionality of X-rays by elimination of those X-rays that do not fulfill the geometric requirements of the detection. And here I want to illustrate this principle. So if we establish collimation, we can use this to select a slice. And this is the only time I'm going to talk for the X-ray techniques about slice selection. So basically, the collimation establishes that only X-rays that are coming in a certain direction or nearly that direction are passing through the detector. And the way we can see it is that we actually are taking the spread, that's our body, And virtually, with this instrument, we're cutting it into slices. That's slice selection as it is being done. Obviously, we're not cutting the live subject. That would not be very practical and admissible. It's done by the instrument. So it's a virtual slice selection. Here, this is real by cutting the slices with a knife, but we're doing it with collimation. We're ensuring that only what is between these two cutting holes is being passed to the detector. And so here in this short video, we are seeing the detection of a CT scan. We're seeing the detector rotate with the source. This is what we'll discuss later this week on how the images are being produced. And as you can see, as the video moves on, you are seeing now how the subject is being moved through the scanner. So actually here the slice selection is being done through the collimation. We're selecting a slice, but instead of having multiple slices that we can select, we are physically moving the patient bed through the scanner, and this generates all these images that are then appearing in the video one by one. So this is a way to generate slice selective information. Now, we will talk about the quantification of contrast to noise ratio. How is this now quantified? The signal is proportional to the intensity as a function of a distance, so it is proportional to the number of photons detected. It is therefore also proportional to the number of photons with which we irradiate the subject. And so the contrast that we get is actually a change in the photon numbers, delta I, as a function of distance due to differences in the linear attenuation coefficient. We have a distribution of the energy spectrum, I of E nu. So the Compton effect, mu Compton, produces reduced contrast. And we have Compton scattering, so this is dealt with the anti-scatter grid. So let's assume we have all this solved. The scattering is eliminated, and we have a way to quantify. Now the thing is here, what I want to point out is we have the intensity, VI0. We have the link here is the linear attenuation coefficient. And so since we can measure the relative, the I of D as a function of I0, we can have an absolute measure of the absorption of the CTs. And this is something where CT, for example, is different from MRI. We have an absolute measure of the CT intensity, and this gives rise to the term CT number. In soft tissue, we typically have weak contrast, and so this is quantified in Hounsfield units. They are small Hounsfield units. And so we'll look here at the CT numbers in terms of Hounsfield units. Now a CT number is the linear attenuation coefficient of the tissue in question minus linear attenuation coefficient of water divided by the linear attenuation coefficient of water, and then the whole thing multiplied by 1,000. What does this mean? This means we're looking at the deviation of the linear attenuation coefficient from that of water, and so this would be a dimensionless unit that gives us the relative deviation, and this is multiplied by 1,000. So it is normalized to water by definition. If mu here is that of water, this is the CT number is 0, and we have a range from minus 1,000 for air to plus 3,000 for bone and contrast agent. Air is at a minus 1,000. Well, air has essentially no linear attenuation coefficient. There are no electrons in air, or very few. The density is very low, so we are getting minus mu water divided by mu water. That's minus 1 times 1,000 is minus 1,000. This is where we have the air down here. And we have the bone here. This is a high electron density, so we have plus, up to plus 3,000. So what does 3,000 mean? 3,000 means that the linear attenuation coefficient of bone is 4 times that of water. 4 minus 1 divided by 1, that gives us 3, times 1,000 gives us 3,000. Now look at all the other tissues and note here the break in the vertical scale. We're looking at Hounsfield units here on the range of essentially from 20 to 60. So these are very small deviations from the linear attenuation coefficient of water. We are obviously primarily water, so water does dominate our contrast. We have breasts, we have fat, there's a lot of fat in breasts, and we have the lung here, which is air, so it's getting close to air. So we have weak Hounsfield units, that means we have not excellent soft tissue contrast. The main contrast mechanisms are air tissue and bone tissue. Those are the strong contrasts that we see in CT images. So we're looking at a range of -300 to +100 for soft tissue.